Hello and welcome. In this video I'll be covering section 8.2, which is over the law of cosines. My goal for you by the end of the video is to be able to, one, be able to use the law of cosines to be able to solve these oblique triangles, but also number two, be able to identify when our approach should be either a law of sines or law of cosines strategy as far as solving a triangle. So hopefully this video will be relatively short and quick, but law of cosines essentially is going to be something that we will utilize if we end up having one of the last two situations I brought up in the last video, which are two sides provided in the angle in between, or the included angle, or if I just give you all three sides to the problem, that's kind of the only way that I can go through and actually solve it. So law of cosines, as you can see, has three different main versions, but really if you just kind of focus your attention on one of them, it's basically whatever the side that you're trying to solve for squared should equal the other two sides squared and added together minus twice those two sides multiplied with the cosine of the angle that's opposite the side that you're trying to solve for. So notice in this case the a squared requires angle A, or b squared requires angle B, or c squared requires angle C inside of the cosine function at some point. But again, the pattern of each of these is I basically will square the other two sides that I know and then subtract twice their product along with cosine of whatever the angle is that's opposite. So to cancel that power of 2, eventually notice what we would need to do is just take a square root, and in this situation we aren't going to need to worry about a plus or minus symbol because context cues will allow us to say, since I'm solving for a side length, I only need the positive version of that square root. Now these specifically are used to solving for sides. So all three of these versions that we have would solve for a side length. So if we needed to actually solve for an angle, what we would need to do is just try and isolate one of those capital letters. So I'm just going to choose the top one, and here kind of at the bottom of the screen I'm going to go ahead and just show how we could start solving for the A, or the capital A specifically, the angle A. So if we look at what we've got the a squared equals b squared plus c squared minus 2bc cosine of a. What I would be able to move are the two squared sides, so b squared and c squared. I could just subtract those over to the other side. That then would give me a new expression, a squared minus b squared minus c squared, being equal to this negative 2bc cosine of a. So to start trying to get the a by itself, or to continue trying to get a by itself, I would go ahead and divide that negative 2bc over. Kind of pushing near the bottom of the screen here, but hopefully you can still see that well enough. But if we look at what that would do, I'm technically dividing by a negative, so what that would do is switch all three of those terms to their opposites. So I'm going to go ahead and switch my b squareds and c squareds from negatives to positive, and then that's also going to switch my a squared to negative conversely. So I'll put the two positive terms first, subtract the one negative term now that I've got, and then now this is going to be over a 2bc, and technically that's now I isolated the cosine of a. So the last step I would do is actually just cancel the cosine with its inverse function, so it would be the arc cosine, or inverse cosine, however you like to say that, of b squared plus c squared minus a squared in the numerator, all over 2bc in the denominator. So again, kind of the rule of thumb here is whatever angle I'm trying to solve for, that's really the only side that I'm going to have subtraction with, and then the other two sides just get squared and added together in the numerator with that minus a squared, and then on the bottom it's twice whatever their product is. So some similarities between the two, but if it helps I'll maybe make this a little bit larger here in the top right. We've got our solution for sides, and then if I needed angles, this will be what I have up here. It's going to be that inverse cosine of, again, the b squared plus c squared, the other two sides, minus the a squared, then all over twice the b times c. And ultimately with that one, it would be important actually for both of these forms that our calculator is in degree mode as per usual. So I would say before you do any typing on a calculator, always do a quick double check of whether you're in the correct mode or not before you waste much time plugging in something that won't ever give you the right answer. So again, degree mode first, and then should be able to type either of these two into our calculator just in one fell swoop, which we'll see some examples of here just in a moment. All right, so let's, without further ado, jump into our first example. So for this one, notice we're given two lowercase letters and a capital letter. They are all three different, so that means I don't have any sides across from angles or vice versa. And in this case, it looks like, again, two of them are lowercase, so I do have two sides. So this is, in fact, a side angle side situation, as it says there in parentheses. So since this is a side angle side, that rules out law of sines. The other reason it rules out law of sines is I didn't actually have any pairs of A's or B's or C's. I just had one of each letter. And I don't have the ability to solve for any other angles just by simply subtracting from 180 or anything like that. So this does kind of force my hand into a law of cosines type approach. So without further ado, let's jump into what the law of cosines would be. I do know angle C, so that does let me solve for side C right off the bat. And it would just be the other two sides squared and add together. So it's 32 plus 71 squared minus twice their product, so 2 times 32 times 71, but also times the cosine of the angle provided, which is the 32.8 degrees. From here, to cancel that power of 2, I would ultimately just take a square root of that result. So as you'll see here when I bring up the calculator, I'm legitimately just going to type this in from left to right with a big square root on all of it and just do it basically in one single step. So let's go ahead and bring that in. Got my square root of, and then it would be my two sides that had, got to remember what those numbers are, darn it. So if I go ahead and switch back, I've got 32, 71, and then 32.8. Okay, so 32 first, 32 squared plus 71 squared minus twice 32 times 71 times cosine of the angle 32.8. And if I go ahead and close that off, looks like that ends up giving me as a final solution here 47.4-ish, I guess 38. Could call that 47.4, and this is a side length, so maybe I'll go out 2 decimal places just to stay accurate. So 47.39. So 47.39 is the value of that angle, or sorry, not angle, but that side length that's across from the angle C. So right now, technically I have all three of the lowercase letters, right? I do have now little a, little b that were given, and I just found the little c, or the side c. So really, I could, if I wanted to, switch over to law of sines if I wanted to finish the problem up that way. My word of caution, if you do switch to law of sines, is you only will be able to solve for acute angles. So you would kind of be forced to look for which side is the smaller of the ones that I have. So I have 32 and 71 as the other two side lengths that are across from angles. So I'd have to go after angle A, just because the inverse sine function does have a restriction of only giving us answers from 0 to 90 degrees. So since the B side is 71, there's a fairly high likelihood that that could come back obtuse, and my calculator would not give me what that obtuse angle is, so I would have to be smart enough to recognize that I would need to find its supplement. Again, all of that probably sounds super confusing, so in the event that you do happen to want to switch to law of sines, just be very, very mindful of always solving for the smaller angle that's left. In this case, the smaller angle is going to be angle A. Now, because this is a law of cosines lesson, I'm going to go ahead and stick with the law of cosines approach, which actually is the safer of the two. If you can avoid switching over, it should give you the ability to find this last angle without needing to worry about solving for a specific one first. But I'm just going to go alphabetical and get A first, and notice again with our kind of shortcut that we made earlier, that just means in the numerator it's going to be that A number squared after the minus sign, and then the other two numbers that I now know, the 71 and the 47.39, will get squared and added in the other spots. So it'd be 71 squared plus the 47.39 squared, then all over twice those same two numbers multiplied together. So 71, that was a weird one. Let's try that again. 71 times the 47.39. And now again, it's going to be something where I'll utilize the ability to type in a fraction template, so I don't have to worry about order of operations as much. But if you wanted to just type it in using division, you'd have to make sure that you throw parentheses around the numerator and parentheses around the denominator like I just added to it. Otherwise, it might just only divide the middle two numbers, the 32 squared and the 2, and then everything else will kind of get a little bit too larger, and it more than likely would give me a domain error if I were to type it in in that way. So again, I'm going to kind of model this using that fraction template and see what this actually turns into, and we'll go ahead and just round it when it's there. So I'll go ahead and get my approximation sign. So again, here I'm going to go ahead and bring in the arc cosine, and then the fraction template, alpha y equals, gets me that top and bottom that I can now use, and I'll go ahead and just type it in. So I've got the 71 squared plus the 47.39 squared minus the a, which was 32 squared. Then all of that will be over 2 times the 71 times the 47.39. And technically I can just press enter there, but I can also close off everything there just by pressing to the right and then closing off the parenthesis. And now when I press enter, it gives me that angle A is approximately 21.5 degrees. So we'll go ahead and call that 21.5 degrees. And so now notice they gave me 3 bits of info. I've total found 2, so really I only have one thing left to get all 6 parts identified. And since the last one is just an angle, I could just take advantage of all triangles add up to 180 and just go ahead and start with 180 and subtract the 2 values I do know, 32.8 degrees that they gave me, and then the 21.5 degrees that I just found. And if I go ahead and type that into the calculator as well, 180 minus the 21.5 minus the 32.8, and that gets me that 125.7 as that last angle. I'm sorry, what do we get there? 125.7. So again, had I switched to law of sines and I tried to solve for that B angle, it more than likely would have given me the supplement of that. So whatever 180 minus that value would have been, which then would have probably thrown off the rest of our answer if we would have used that to come up with what angle A was. So the safer route through is if you start with law of cosines, just stick to it until you can get at least 2 out of the 3 angles. Then you can find the last one just by subtracting from 180, and that would be how you find your obtuse angle. Or if we wanted to, we could have done this same thing for angle B. I just would have had the 71 squared after the subtraction sign, so if we wanted to see what that would look like, the angle B also could have just been the arc cosine of the 2 other angles, so 32 squared plus 47.39 squared, but then again minus the angle that's across from, minus the side that's across from this angle, so B in this case was the 71, so that's the only thing I'd be subtracting in the numerator. Then twice the product, sorry I forgot my power of 2 on that 47.39, and it would be twice 32 times the 47.39. This one doesn't need the power. And just type that in the calculator and you would notice that it would actually turn into that same obtuse value. And that's just because the arc cosine actually does allow our answers to go from 0 to 180, hence why it would be okay if you solve for the obtuse angle with this. It's just with law of sines, you have to be very, very mindful of that function does have that restriction, so just be careful if you do happen to switch. But again, first example, hopefully you can kind of see like how the moving parts work. It really is more difficult just with the typing into the calculator probably more than anything, and it just takes a little bit of repetition, and the more you see and use this formula, the easier it is to recall where the parts are supposed to go. Moving on to another example, this one would be more of the what if I gave you just side lengths. So with this one, notice I'm giving you 3 lowercase letters, so that is truly a trio of sides. So really the only thing left I have to solve for are just the 3 actual angles. So we can kind of choose which angle we want to solve for first. With this being R, S, and T, I think I'll just solve for R. I'll just go alphabetical. And we've already kind of set up that kind of shortcut for this formula. It's going to be the arc cosine, just like we did to finish the last problem, of, and I know there's a fraction on the inside, and at the end, the subtraction needs to match the same letter. So I know for sure the R, which is 3.5, is going to be the number squared and subtracted in the numerator, and then it's just the other 2 numbers in whatever order really you want, squared and added together in front of it. So I'll just go with 4.7 first, squared, and then 2.8 squared there in the middle, and then on the bottom it's just twice those same 2 numbers, 4.7 and 2.8. And as mentioned before, we'd go ahead and just bring our calculator up. I'll clear out all that stuff from the previous problem and just do the arc cosine of, and then create my fraction template. So again, alpha y equals, and just press enter, and that gives me now this template that we can go with. And we had the 4.7, I think I wrote first, squared, added with the 2.8 being squared. Then I take away the 3.5 that's squared and put it all over twice the 4.7 and 2.8 all multiplied together. And again, I'll just press enter. You don't have to close off that parenthesis, but I guess proper notation would be to do that. But regardless, we get this value here for angle R of 47.8 degrees. So we'll go ahead and switch back to the answer here, 47.8 degrees. And again, we are finding all of the angles with this one, so every answer that we're going to get should have a degree symbol on it. Now from here we have the option. We can choose to go with angle S or angle T next. I'll just continue through the sequence and know that it's going to be angle S next. If I wanted to, I could switch to a law of sines approach since I now have both R's. And if I did do that, I would actually avoid solving for S since that's actually the biggest side. It's a high likelihood this might come back obtuse. So if I were to switch to law of sines, I would make sure to solve for T next. And then once I had the two angles, I just add them up and subtract from 180, or just subtract them in sequence from 180, and that would give me what's remaining for that last angle, in this case angle S, if I had made that switch. But I'm going to go ahead and stick with this law of cosines idea. S is the 4.7 side, so I'm going to make sure that that just goes after the minus sign, and then the other two numbers just go in whichever order you would like. So I'll go with 3.5 squared added with 2.8 squared, and then on the bottom twice the same two numbers multiplied together. So 3.5, 2.8 in the denominator, and let's go ahead and see what that turns into on the calculator. So again, starts with inverse cosine or arc cosine. Get my template, and now I've got the 3.5 being squared added with the 2.8 being squared, subtract the 4.7 squared, and then all over twice the 3.5 and 2.8, which are the first two numbers before the plus sign, or sorry, the minus sign on the top. And again, press enter, gives me an obtuse angle. So yeah, had I switched to law of sines, it would have probably given me like an 84 degree angle instead of this 95.6 that it's supposed to be. Or not 6, but 95.9. There we go, if I could say it. So 95.9 is the second angle we've been able to find. So now to get angle T, I could just do the simple, let's just subtract those two in sequence from 180. And see what that turns into. So 180 minus the 95.9 minus the 47.8. And that gets me that 36.3 is all that's left for that last angle. Now we could have also just continued with the law of cosines if I wanted to. The last one, if I would just kind of model it here on the calculator, it would be the arc cosine of, bring in the template. And again, the only thing I know I would be subtracting is going to be the 2.8, so it would just be the other two numbers squared and added first, so 3.5 squared plus the 4.7 squared. Then it would be minus the side that's across from this, so 2.8 squared over twice the 3.5 and the 4.7. If I press enter, notice it gives me an answer. 36.3 is more than likely what we wrote it rounded to there. So again, either way we wanted to get that last one, it still would work. So you could just continue and just do all three angles using law of cosines, or once you have two, you can trust that your other work was accurate, and you can go ahead and just subtract them both from 180. And again, hopefully this is proof positive that it gives you the same answer regardless. I think that subtracting from 180 is a little bit more efficient, but you know, to each their own. All right, the last skill, just to practice, I suppose, or to kind of give you an idea of how you can narrow this down, is just being able to choose the correct strategy from the get-go. So again, our two main strategies with these oblique or non-right triangles is law of sines or law of cosines, and ultimately what you do is just kind of look at what's been provided, and I think probably the easiest way to think of it is if I don't have any pairs that line up, that kind of rules out law of sines and leaves law of cosines as the only option. But you can also just kind of memorize which out of the cases would work. Law of sines is always going to be the angle side, or the angle side angle, or the side angle. One of those three cases is always going to go with the law of sines. And then law of cosines, this one is specifically the side angle side or the side. So if you just wanted to kind of memorize those things. Just remember the side-side angle is always that ambiguous case. It may have a solution. It may have two solutions. It may not have a solution at all. But ultimately, with this, it's just kind of coming up with how should I even start the problem is really what this is having us practice. So if we look at the first one, notice we have 3 lowercase letters, so really I don't have any angles at all, so that really rules out law of sines because I need to have at least one angle involved there. So that does force my hand into the law of cosines. Let's just go with cosines or sines. I think that's probably going to be more efficient. So law of cosines for part A. Part B, if we look at that one, or number B, or letter B, it looks like I've got 3 different letters this time, but 2 of them are capitals. So if that's ever 2 angles, that right there is going to tell us that we're going to just use law of sines, because I should have the ability to find angle A, and then once I have angle A, I have at least one of the ratios set up where there's no variables left. So sine of A over the 207 would able to be found, and then I could then use that to either set up an expression for the B or C side just one at a time using law of sines. Next one, if we look at what we've got 2 that match. I have 2 A's, so for sure that's a law of sines, but the other dead giveaway is I gave you 2 angles as well, so I could have found the third in the event that I didn't have something match up, but again, 2 A's for sure guarantees law of sines would be my approach. Moving on to the next one, it looks like I've got a capital B, lowercase a, and a lowercase c. So none of those paired up, so for sure law of sines seems like I wouldn't be able to do. I only have the one angle, so that would kind of force our hand into law of cosines. Even if we tried setting up, like I said, the law of sines, we would hopefully recognize pretty quick that every single one of those ratios still has a variable left, so wouldn't really be able to use that to solve for anything. But anyway, 2 more to go. We got for the next one side E, side A, and then angle A. So once again I have 2 A's involved for this one, so that would be a law of sines because I have that ratio set up. That would then let me solve for angle E next, and then once I have angle E I could get whatever the last lettered would be. I don't know where they would be going with that one, having A and E together, but we can make up whatever the last letter is unless they gave us the name of the triangle, and that would let us solve for that third angle. And once they have the third angle, we could then get the third side using all law of sines from start to finish. The last one is kind of a trick, but if I give you all 3 angles, technically if I assign this to, say, a group of 5 different students, all 5 of those students could technically draw the same triangle but at completely different sizes because there is no side provided. I have no idea what the scale would be, so this actually would be one of those situations where it would not be a solvable triangle because I have not established how large any of the sides would be, so there's no ability to use a ratio or trigonometry to actually solve that triangle. So if you only have angles, so in other words AAA is not really an option when it comes to trying to solve a triangle. Anyway, hopefully this has been a helpful video. Hopefully it was a lot shorter than the last one, but as always, if you have some questions, by all means just ask whenever you see me or come seek me out, and I'll try and walk you through any confusion that you may have. But as always, I appreciate you taking the time watching the video, and we'll catch you next time.